Welcome to this movie on statistical mechanics. My name is Jos Thijssen and I teach statistical mechanics at the Technical University of Delft to applied physics master students. In this movie I want to address renormalization theory for critical phase transitions. And critical phase transitions exhibit a very weird behavior which is characterized by all kinds of divergencies. And those divergencies are quantified by critical exponents. And I want to address in this movie merely the main feature of renormalization theory, which explains how these different critical exponents are related. To explain the renormalization theory for critical phase transitions, we will keep a very general approach, but on the other hand we will illustrate it using the Ising model, and the Ising model is a model with spins, and these spins can take on two different values, +1 or -1, and there is a nearest neighbor interaction which tries to keep the spins aligned. So if there is a plus at a side of the lattice, then the neighboring sides also want to be plus, but the temperature will compete. So this is the simulation where you can see the Ising model. The blue ones are, for example, the plus ones, and the red ones are the minus ones, and you see that we are now in the high temperature phase. You can see that here from the coupling constant in the terminal window. This is a low value of the coupling constant. It includes the factor beta, which is 1/kT, so it means high temperature. If this guy gets larger, the temperature goes down. And you see that the area covered on average by the red spins is more or less equal to the area covered by the blue spins, but you see large fluctuations. Also you see, and that's really important, that you have islands of all possible sizes. You have single spins that are flipped, you have islands, clusters of small spins that have one color, and now you see that you get even clusters which have the same size as the lattice, and that's because we are approaching the critical point. The critical point is now, it's 0.44 for the coupling constant. That's very close to the value of the critical phase transition. And now we are at lower temperatures, we are below the phase transitions. The red guys dominate and the blue ones will never come back. So there is now a majority spin. The important message that I want to convey with this movie is that we have fluctuations on all possible scales. I will now try to make a cartoon of what we have just seen, and first of all it's important to realize that I'm not going to do that in a detailed way, so I'm not going to reflect the square structure of the underlying lattice. We are looking through our eyelashes and then we see a kind of coarse-grained structure. And let's start with a big red region, and so this is the boundary of the red region that you could observe in this simulation. Now within such a red region, so imagine that everything inside the red line here was colored red, but inside the red region we had these blue blobs which look like this. And they were not only large blue blobs, we have seen that there were also small islands. There were also smaller islands of blue blobs, and there were even single spins that were reversed. So they were blue within, so everything inside the red one is inside the red curve is red until we reach a blue line, and then everything inside is blue. So let's draw a few other blue islands. And then within these blue islands we could see that there were again red areas. So we have islands within islands, or droplets within droplets. And even here I can find very small red excitations also here. And then within the red ones we have blue ones, etc., etc. And so the main message here is that the fluctuations, the deviations of the spins from the average value in a certain region occur at all length scales. So the system seems to have some scale invariance, and it's the scale invariance which forms the basis of the idea of renormalization theory. In a previous movie I've already introduced critical phenomena, and there we have met the so-called critical exponents, which quantize the non-analytic behavior that we see in different physical quantities in the thermodynamic limit when we approach the critical temperature. The critical temperature is Tc, and for example, if we have here a positive exponent alpha, then we see that when T hits Tc, the specific heat, C at constant magnetic field, diverges. The magnetic field, by the way, should be zero, because otherwise we have no critical behavior. Also important is this guy, that's the correlation length, and we see that the correlation length also diverges with the critical exponents nu. Then we have the magnetization, which vanishes when we approach Tc from below with some exponent beta. We have the magnetization, the magnetic susceptibility, which tells us how the magnetization varies with changing field, and that also diverges. We have the variation of the field of the magnetization with the field itself at a critical point, and we have the correlation function. And so we have 1, 2, 3, 4, 5, 6 critical exponents. Now there are some weird features associated with these critical exponents. First of all, they all are in 2 dimensions, rather simple rational numbers. And the second one is that they seem to be related. So if I go from one model to another, I find different critical exponents, but there are several relations between them that always seem to hold. And it's precisely that point, these scaling relations between the critical exponents, that is addressed using renormalization theory. In that renormalization theory, we try to exploit the scale invariance of the system, and we do that by starting with an Ising lattice formulated on a square lattice. So here we have a square lattice, there are Ising spins on each side, and what we want to do is we want to map this system onto a coarse-grained system, and we do that as follows. We identify plaquettes in the lattice like this, and these plaquettes, they are separated by a lattice constant, and so we have spins at each of the black crosses, but we want to replace those by new spins that live at the center of each plaquette. So we are going to introduce new spins that live on the red crosses, and we see that the red crosses are 2 lattice constants apart, 2 original lattice constants apart. Now we call the original spins on the fine-grained lattice Si, and the spin that is found on the red crosses, that's called Tk. So K identifies the side, and Tk is the spin on that side. Here we have an enlarged view of such a plaquette, which is surrounded by 4 fine-grained spins, S1 to S4, and in the center of the plaquette we find our new spin Tk, and we want our new spin to have the same, to assume the same values as the original spin. So that is Tk can assume the values plus or minus 1, just like the Sk. So how do we choose the value of the Tk? Well, we use a very reasonable recipe for this. If the sum of the spins surrounding Tk is positive, so if the majority of the spins is plus 1, then Tk will also be plus 1. If the majority is negative, so there is a majority of minus 1 spins, then the Tk will also take the value minus 1. So either there are 4 spins plus or there are 3 spins plus, and then we choose Tk to be plus 1, or there are 3 spins minus or 4 spins minus, and then Tk is minus 1. So what do we do if we have 2 spins plus 1 and 2 spins minus 1? Well, then we don't prescribe the value of tk, but we just choose at random a plus or a minus with equal probabilities, because there's no preference or no reason to give a preference to +1 or to -1. So it seems like a slightly arbitrary recipe, but it makes sense, as we will see. We can formulate the recipe in terms of a probability density W, and W is a function of tk and the 4 surrounding spins. We suppose that the 4 surrounding spins have given values, and then if those given values add up to a positive number, then the probability to have tk is 1 is 1. And of course, if the sum of the spins is negative, then the probability to have tk minus 1 is 1. If the sum of the spins is 0, so we have 2 pluses and 2 minuses, then the probability to have a tk plus 1 or minus 1 is in both cases 1/2. And we see that for any given set of s's, if we sum over the two possibilities for tk, then it always ends up to 1. So if the s's, for example, add up to a positive number, one of the values is 1 and the other one is 0. So the probability to have a tk minus 1 is 0 in that case, and so the sum of 1 and 0 is 1. The same here, and here we add up half and half, and that also adds up to 1. So for a fixed set of s spins, the sum of the probabilities to have tk plus or minus is 1. Simply because tk always will get some value, either plus 1 or minus 1. Now we define a new Hamiltonian, which is not defined in terms of the s spins, the original spins, but in terms of the new spins tk. So we have now a Hamiltonian which describes the system in terms of the coarse-grained spins, the tk, which are found at the centers of the plaquette, of the red plaquettes in this picture. So here is a tk, here there is a tk, and we try now to find a Hamiltonian in terms of these new variables tk. Here is my new Hamiltonian. It's defined as follows. We take first the Boltzmann factor of the original model. So we have a configuration of fine spins, Si. I have left out the K superscript here because it's simply all the spins in the system. We calculate the appropriate Boltzmann weight, and we sum over all the possible configurations of spins in the system, so all the spins being plus or minus. And then we multiply this by the WTK, so that means that if at plaquette K, for example, the spins add up to a positive number, this will be 1, negative it will be minus 1, or it will be plus or minus 1, with equal probabilities if the sum of the s's is 0. And the resulting expression, because I've summed over all the configurations of fine-grained spins over the lattice, will only depend on this tk. That will be the only dependence in the final expression. So this new Hamiltonian, which I should give a big prime, it's the new Hamiltonian that is defined in terms of the tk and not in terms of the s's. And having this new Hamiltonian in terms of the tk, I should not forget the prime here, it's not so difficult to calculate the new partition function. I just sum over all the tk's and I get this expression. And now I fill in the definition of this new Hamiltonian. So here I have to sum over the sik's being plus or minus 1. And then here is my e to the power beta minus beta h in terms of the fine-grained spins. And here I have the w. Now I have a sum over the tk's and I have a sum over the sk's. And I can swap those two sums. So if I swap the two expressions, I first have a sum over the s and then I have a sum over the tk. I moreover move the w in front of the Boltzmann factor here. And the reason why I did this is that we have already encountered precisely this sum. So this is the only place where there is a tk dependence, so I can work out this sum over tk. And scrolling back we had seen that that sum over the TKs of the W for any configurations or a configuration of the S's adds up to 1. So if I take any configurations of S's here and I work out this sum, it just gives me a 1. So I can leave it out from this expression, and then we see that what I end up with is just the sum over S and then the Boltzmann factor of the Hamiltonian in terms of those S's, and that was the original partition function. So we see that the partition function for the TKs is exactly the same as the partition function for the S's, and so we have succeeded in reformulating the problem in terms of the TKs such that the partition function and therefore the thermodynamic behavior is the same for both models. So transforming from the fine spins S to the coarse spins T leaves the partition function invariant. That's the conclusion we can draw. So we carry out the procedure that we have outlined above. So we, for any fine-grained configuration Si, we construct a coarse-grained configuration using the W function that we have defined above, and then we find a Hamiltonian which describes the interaction between the TKs. And now that will have some arbitrary form. It does not necessarily have the same form as this Hamiltonian, but we assume that there are two dominant terms, which are a nearest neighbor coupling between the coarse-grained spins and the next nearest neighbor coupling between the coarse-grained spins. And then there may be several other terms in this Hamiltonian, for example, terms coupling 3 or 4 spins, and we assume that we can neglect those. So what we do is we just truncate the Hamiltonian beyond the terms that were already present in the original Hamiltonian. Whether that's a justified procedure is not known at this stage, but I will come back to that at a later stage. What is important is that if we do this procedure, the J is not guaranteed to remain the same. It may change its value. For example, if we are in a high temperature phase, and there is already a weak coupling between the Si and the Sj, if we then take plaquette spins that are even farther apart, it's likely that this J primed is going to be smaller than the J. And the same obviously holds for the K. So the J and the K map onto new values J primed and K primed. And given the fact that such a mapping exists, it means that when we start from a point Jk in the Jk space, the renormalization transformation will map us onto new values J primed and K primed, and that gives a flow. So from each point we move to another one, and then we move again to another one if we would carry out another renormalization transformation, and so we move from point to point. Before studying that flow, let's make a few remarks. We take first of all the magnetic field equal to 0, because otherwise we wouldn't have a critical system. The criticality ceases to exist when B is non-zero. But later we will consider weak fields. But for now we take B as 0. Then we should realize that if we go from the fine-grained spins to the coarse-grained spins, we have a new lattice constant, which in the example that I have illustrated above, let's scroll back. There this rescaling factor was 2. The new lattice constant between the red spins is twice as big as the original one between the black spins, and so for any such transition, it doesn't have to be exactly the one that I have illustrated here, but for any transition we have a rescaling factor. It may be 2, it may be 3, it may be 4, and we call it in general L. So the new lattice constant is L times the old lattice constant, and L is called the rescaling length. So here we see the renormalization flow, and obviously this picture needs some clarification. So let us first realize that if we go from one point to another point, like we move from here to there, that is what happens when we go from fine-grained spins to coarse-grained spins. Now, the points where the coupling constants are very large, That's the low temperature point. So this is low temperature, and I've just indicated it here as one single point, but in fact this is the value where k and j are infinite. When k and j are 0, we have a very high temperature, so then the temperature is infinite. So this is the high temperature point. And now let's see what we expect close to the low and the high temperature point. Let's start with the low temperature point. At low temperatures, the vast majority of the spins is the same. Say it's +1, and there are small islands of -1s. So whenever we go from the SI to the TK, if we consider a lattice plaquette, it's almost impossible that there are two s's which are -1, because the probability to have an s which deviates from the majority value of +1 on the lattice, that probability is very small. So if we have two s's which would be -1, that's exceedingly small. So there is a very, very, very big probability, very close to 1, that the TK in this plaquette would also be +1. So because everywhere in the lattice there is a vast majority of +1 spins, all the TKs will become +1. So they will become even stronger +1 than the SK already were. And that means that we are going from a low temperature phase with a majority of +1s to an even lower temperature phase, because the TKs have a higher probability to be +1. So let me repeat that argument. So if there are 4 pluses here, then it's clear the TK will be plus. Now we may be in a situation that we have 1 minus, but that's already rare, because the vast majority of spins in the low temperature phase characterized by positive magnetization is +1. So this is already rare. Let's say that there's a very small probability P. Now the probability that we have 2 minuses on the lattice, that's even a lot smaller. It's of the order of P squared. And so in fact the probability that the TKs would be, and even if there would be 2 spins that would be minus, then there would still be only half a probability that the TK would be -1. So all in all, we see that the probability for the TK to be -1 is much smaller than the probability for these individual s's to be -1. And so the TKs are more strongly +1 than the s are. That means that we are moving towards lower temperature, and that explains the direction of these arrows. If we are close to the low temperature phase, renormalization will make that the system will be only lower temperature, only more low temperature. Another way to see that is imagine the simulation I showed you before with the red and the blue spins. If the vast majority is red, what it is, as is a situation below the phase transition, and I would squeeze my eyes, then I would probably no longer see the blue ones. I only see red. And that's precisely what the renormalization transformation means. You are in fact squeezing your eyes, you're looking through your eyelashes, so you don't see the details anymore. You only see the coarse grain behavior, and that is completely red. So you are in a lower temperature phase than you started off with, when you were still looking clearly at all the details of the lattice. So how is that in the high temperature phase? If we are here at not infinite but high temperatures, we have islands of a small size which can be plus or minus, and in fact it's kind of patchwork, the entire system. So the entire system is composed of clusters that are blue, clusters that are red. And now we are going to coarse grain, and because the lattice constant of the coarse grain lattice is getting larger, the effective size of the domains of one spin measured in units of that lattice constant is getting smaller. So to illustrate that, suppose I have a red blob in the system, and that has a certain size, the size psi, measured in lattice constants of the fine-grained system. And then I'm going to make the lattice constant twice as big, and I'm measuring the size here in terms of the lattice constant, so then it will be in terms of the new unit of distance, which is the lattice constant. The psi will become twice as small, which means that effectively the blobs are going to be smaller, and the smaller the blobs, the higher the temperature. And so that explains why, when we are at high temperature, the renormalization transformation brings me to even higher temperatures. Now, these are rather subtle arguments, so let me repeat them for clarity. So in the low temperature phase, we have a majority of say, red spins with small islands of blue spins. If I'm going to look at the average spins on larger areas, it's almost certainly going to be red, and the bluishness of the lattice is going to be reduced. And when the lattice is becoming more and more homogeneously filled with one color, it means we are going to lower temperature. If we are at high temperatures, we have domains of a certain size, which can be blue and red. They just alternate. And if we are doing a renormalization transformation, then measured in the new lattice constant, which is twice as big or L times as big as the original ones, we see that the domains shrink. And shrinking domains means that we are going to high temperature, because the situation is going to be more and more chaotic. Now, given this trend of low temperature flow towards this point and high temperature flow towards that point, the only possibility for the remainder is that there is some line which separates the high temperature region from the low temperature region. And by continuity, the flow at that line should be like this. And so that completes the renormalization flow in a qualitative sense. And what is very important here is that usually if on this line, it is possible that we find a so-called fixed point. And in a fixed point, if we are there, then the system doesn't change anymore upon renormalization. So the effective coupling constant for the coarse-grained spins turns out to be the same as the effective coupling constant for the fine-grained spins. So here once more, for the last time, a summary. T low goes to even lower temperature under renormalization by a rescaling length L, and the high temperature goes to even higher temperature. Now, the argument for the high temperature involved a correlation length. So the correlation length psi is the average size of the region of +1 or -1 spin. So it's a region of one color in the simulation, red or blue. And I have already sketched that if we change the lattice constant, and that's what we do when we rescale the lattice, then it turns out that that affects the psi, because psi is measured in units of the lattice constant. If the lattice constant is going to become bigger, as it does under the renormalization transformation, effectively the psi measured in those units gets smaller. So we can now make a quantitative statement. If we scale the system by a factor L, above that was a factor 2 in the square lattice, but generally it's a factor of L. That implies that the new correlation length, which is the correlation length corresponding to the new coupling constants, it's the old correlation length, because the psi, which is the size of a domain, that doesn't change, but it's measured in different units, and so we have to divide by L. So this is a very important formula. We need a similar formula for the free energy. And the free energy F is an extensive quantity, so it scales with the number of sites in the lattice. So F is proportional to n, where n is the number of sites. Now we want to go to an intensive quantity, which is the free energy per lattice site. so if we define the free energy per site as small f is the capital F divided by n, then this obviously doesn't change with the lattice becoming bigger. Now, before we have seen that if I perform such a renormalization transformation, the partition function doesn't change. So if I look at the partition function with the new coupling constants, and the size of the lattice is no longer the original size, but it's the original size divided by L to the power d. D is the dimension, so if I started off with n points and I have a rescaling length of L, then n divided by L to the power d is the new lattice size. So that's the number of k spins which I had if I started off with n s spins. And so the j and the k, they go to the j primed and the k primed. That's just the renormalization transformation. So what we can infer from this is the following. The free energy is directly defined in terms of that partition function. So if the partition functions are the same, then the free energies are the same. And if I then consider the free energy per lattice site, I should divide the free energy by the number of sites, in this case of the number of t spins, which is n divided by L to the power d. And so I can put the L to the power d in front of this, and I get L to the power d times f jk, which is equal to the renormalized f. And if I divide that by n, I see that I have the following relation. The new free energy per lattice site expressed in terms of the coupling constants j primed, k primed, is L to the power d times the old free energy per lattice site. So that is before renormalization. So the scaling factor for the free energy is L to the power d. So before we proceed, it's good to summarize what we have so far. The correlation length scales with 1 over L when we go from the old to the new system, from the fine grain to the coarse grain system. And what happens to the free energy? It is scaled by an extra factor of L to the power d. Now it turns out that the qualitative structure of this picture, together with these two relations, gives us extremely useful information about the critical exponents. First of all, we identify this fixed point here in the center of the mapping, and we call it J star K star. So J star K star are the two components of the fixed point. And in order to analyze the behavior close to the fixed point, we define a J, which is J star plus delta J. So that's a point which deviates a little bit from the fixed point. And we want, in order to study the flow, we need to know what happens to this delta J and the delta K. So we are going to do now the renormalization transformation. And then we will find, well, obviously J star maps onto J star. So the new point will still be in the vicinity of the fixed point, but the delta J has changed a little bit. That's now a delta J primed, and the delta K likewise, that will be a delta K primed. Now, to a first order Taylor expansion, we can expect that the relation between delta J primed and delta K primed is linear, which is expressed by this formula, where we have here the vector delta J primed, delta K primed, which is linearly related to delta J and delta K. A is a 2 by 2 matrix. So A is just a 2 by 2 matrix, which relates the deviations after the renormalization transformation to the deviations from the fixed point before. And if we diagonalize that matrix A, we find useful information about the mapping. We find two eigenvalues, lambda and mu, And if we inspect the flow diagram, we can identify those the eigenvectors corresponding to those, because we expect that a vector that is pointing in this direction will become larger but not change its value too much. So there should be a vector in the vicinity of this one, which is the eigenvalue, and you see that it will grow because we move away from the fixed point. So there will be one eigenvalue, and that's mu, which is larger than 1. It's the same if I look at minus that eigenvalue, eigenvector. Of course it will have the same eigenvector, and it will move in that direction, so the mu is larger than 1. On the other hand, there is a direction along the line, here along the fixed line, and we see that points on the fixed line, they move back towards the fixed point, which means that the delta j primed, k primed are smaller than these guys, and so they correspond to an eigenvalue lambda which is smaller than 1. So the lambda corresponds to the fixed line, and the mu corresponds to a direction independent, perhaps perpendicular to the fixed line. Now let's see what happens if we would apply two renormalization transformations in succession. So we have the eigenvalues lambda and mu, and obviously they depend on the rescaling length. Now what we could do is apply two renormalization transformations, so that means that we rescale twice, and so that corresponds to a rescaling length not of L but of L squared. So the rescaling length in that case is L squared. If I look what happens to the eigenvalues, if I apply the renormalization transformation twice, I apply in fact the matrix A twice. So I have A squared, and the eigenvalues of A squared are lambda squared and mu squared. So what we can conclude is that the lambda of L squared is lambda of L squared, and we have the same property for mu. And from this we can conclude that lambda should have the form L in the power y, and mu is L in the power z. And because lambda is smaller than 1, we have y smaller than 0, and we have z positive. These numbers y and z are extremely important. They are called the scaling dimensions. So they are the exponents of the expressions for lambda and mu in terms of L. Lambda is L to the power y, and mu is L to the power z. Scaling dimensions, and we see that one of those is positive and the other one is negative. So going back to the flow diagram where I see the fixed point, I've drawn here two unit vectors, and they are the eigenvectors of this transformation A. There is the eigenvector t, which points in this direction and which corresponds to the eigenvalue bigger than 1, because it is moving away from the fixed point. And we have the eigenvector s, which moves along the fixed line, and once I move away from the fixed point I go back, so that corresponds to my lambda, which was smaller than 1. And so instead of using k and j, I can also express each point here in terms of these new eigenvectors that I use as basis vectors t and s. In other words, we can write any vector in the jk plane, and in particular the vectors close to the fixed point, as v vector is t times t hat plus s times s hat, because the two eigenvectors form a basis. And so we can at will switch from the representation jk to the representation ts, where t and s, not being vectors, are just the coefficients of this expansion. And just as a reminder, I have put here that s hat and t hat are the eigenvectors corresponding to lambda and mu, the two eigenvalues of the matrix A. So if we take our matrix A and we act on this general vector S times S hat plus T times T hat, the S hat will transform according to lambda, it's the eigenvalue of S, and mu is the eigenvalue for T, and we have seen that we can write those eigenvalues as L to the power Y, L to the power Z. So what happens if we apply a n times? Then we have lambda to the power n and mu to the power n, and we find S, L, Y, n, and here we find T times L to the power Zn. So this is after n times applying the renormalization transformation. And so we can conclude that the coefficient of S after n transformations is given by the original S times L to the power yn, and the same for T. After n transformations, the coefficient T moves over to T times L to the power Z times n. Recall that we had derived the following property for the xi's under renormalization. The xi goes down by a factor of L when we perform a renormalization, and that was formulated in terms of the j and the k, but obviously we can do exactly the same in terms of the s and the t, because they are just a reparametrization of the j and the k. Now let's see what happens if we perform the renormalization transformation n time. Well, in that case the coefficient s is rescaled by this L to the power yn. That's what we see here, and the t is rescaled by L to the power nz, and because we have performed n renormalization transformations, the xi goes down by a factor of L to the power n. And now we are going to apply a special trick. We are starting off close to the fixed point, which means that the s and the t are very small, but after many rescalings I could, with this eigenvalue t, or eigenvector t, which has a eigenvalue which is bigger than 1, I could move arbitrarily far away, and so I take n large such that t times L to the power nz is equal to 1. So let's go back to this picture in the flow diagram. I start off very close to the fixed point, and then I have so many renormalization transformations. So in the beginning I move away very slowly, because the t initial is very small, and it grows and it grows and it grows until it has reached the value 1. So the coefficient of the point in this direction grows until it has a value 1. Then I can conclude the following: because L to the power n can be written as t to the power minus 1 over z, I can put this t to the power minus 1 over z raised to the power y in front of s, and then here I have 1 because L to the power nz t was taken to be 1, and that's xi for an arbitrary s and t times t to the power 1 over z, where the last term derives again from this relation. L to the power n is t to the power minus 1 over z. So let us see what happens to this. The y was smaller than 0, it's negative, s is positive, so this is t raised to a positive power, and I multiply that by s, which was very small. T was also small, so approximately this first quantity here equals 0. And so I can conclude that xi as a function of s and t scales as t to the power minus 1 over z times xi, and then taken at 0, 1. So that's this left hand side. I've reversed left and right hand side and multiplied by t to the power minus 1 over z. This is just a number. It's the given correlation length at the point 0, 1, and we see that if I move closer and closer to the fixed point, I find this dependence, t to the power minus 1 over z. Now, going back to the flow diagram, it's clear that this direction here, it changes the value of k and j. Now k and j are fixed coupling constants, but they include the factor beta, which is 1 over t, and that means that k and j include the temperature. So moving in this direction means that I'm changing the temperature. This is the temperature direction. This direction is the direction which corresponds to changing the relative importance of the nearest neighbor and the next nearest neighbor coupling. But this is the temperature. And so this parameter t, which is the parameter along this line, I can safely identify that with T minus Tc. At least it should be proportional to T minus Tc. And so what we find is that the psi therefore scales as 1 over T minus Tc to the power 1 over z, and by definition this scales, the psi scales as T minus Tc in the power minus nu. That was the critical exponent which was defined beforehand in order to describe the divergence of the correlation length. And so what we find therefore is that nu is 1 over z. So what we have seen is that if we perform a renormalization transformation, we linearize it around a fixed point and we calculate the eigenvalues of the linearized transformation, then these eigenvalues via the critical dimensions, in this case the z, tell us something about a critical exponent, which is nu. Now recall that this is just a global discussion about critical phenomena, and we don't want to be specific with respect to the renormalization transformation or the model. So that means that dz is for us a completely unknown quantity, so we haven't obtained any information about nu. Nevertheless, if we combine this result with other results that we are about to derive now, it turns out that we find very useful relations. After having obtained this result, let's look at the free energy per site, which, as we have seen before, scales as follows. If we start with the free energy per site in the fine model, then in the coarse-grained model we have the same but scaled with a factor L to the power d. First we extend this model with a small magnetic field H. In that case the Hamiltonian becomes the old Hamiltonian, and then there is this extra term H sum over I SI, which accounts for the magnetic field. As we then move from 2 variables j and k to 3 variables, so in addition to j and k we now have the variable H, it is clear that the matrix A now becomes a 3 by 3 matrix, and hence we have 3 eigenvalues, 2 corresponding to the jk plane, those are the ones that we have seen before, lambda and mu, and then there is one which is kappa, and kappa is a third eigenvalue, and it's associated with switching on a magnetic field. Now if the kappa would be smaller than 1, it would mean that if we switch on a magnetic field, that renormalization brings us back to the zero field case. It would mean that the term associated with the magnetic field would shrink under renormalization, but because we know that the critical behavior is destroyed when we switch on a magnetic field, we anticipate that kappa is larger than 1. Well, previously we had already seen that lambda and mu can be written as L to the power y, L to the power z, respectively. And so for k we choose L to the power v, which is the third critical dimension. And because the kappa is expected to be larger than 1, the v is larger than 0. Y is of course still smaller than 0, it's negative, and z is positive. The scaling argument for the free energy is still valid, It's not affected by the introduction of a third term in the Hamiltonian, so we still have the scaling of L to the power d. And if we exploit that for performing n transformations, where each transformation gives you an eigenvalue in case of S of L to the power y, so now we have L to the power ny. For the t I have L to the power nz, and for h I have L to the power nv, and that should be L to the power nd times f sth. So this is the scaling relation after rescaling n times. And now we play exactly the same game as before. We take t small, so it's close to the fixed point, and n large, such that L to the power nz times t is 1, and then we find that L to the power ny times s is going to 0, and so s will become 0 after many transformations, and the t will go to 1. Now let's first take the field equal to 0, so h is 0. Then we find that f st 0 is L to the power minus nd times f 0, 1, 0. So it's the inverse of this relation, and here we have a 0, here we have a 1, and we took h from the start strictly 0, so there's no way to bring that to a large value, so that's a 0 here too. And again we see that we have a relation for f in terms of a number. f0, 1, 0 is just a number, and there is a scaling factor before that, which is minus nd. And because we know that L to the power minus n is t to the power 1 over z, we can write that as t in the power d over z. And you should recall that t is the deviation from the critical temperature. Having the free energy, we can obtain the specific heat. So that's in fact our aim, and we get that as follows. The entropy can be shown to be equal to df dt. F is E minus Ts. And then we find the specific heat at constant magnetic field as T times ds dt. That's the definition. And so we find that as T times the second derivative of F with respect to the temperature. And we should realize that it doesn't matter whether we take the derivative with respect to the little t or with respect to the large T, because Tc is a constant. So using that, we see that we get the second derivative of f with respect to t, and so that gives us a prefactor of t in the power t d over z minus 2. By the way, the factor there is of course also a t in front of this doesn't matter, because that's close to the critical temperature, so I can safely replace that by the critical temperature. And we know that's by definition that the c at constant field is given by t to the power minus alpha. That's the definition of the critical exponent alpha. And so we have found, using mu is 1 over z, that we found in the context of the correlation length, that the critical exponent alpha is given by 2 minus d times nu. And this is the first example of a scaling relation, which is a relation between the critical exponents. Now it's important that this scaling relation only involves the dimension and the critical exponents themselves. It does not involve the scaling dimensions. Those are the numbers y, z, and v. So the numbers that occur in the eigenvalues of the renormalization transformation close to the fixed point. They are just relations between the critical exponents, and they are independent of the specific eigenvalues that we find in diagonalizing our matrix A. So let us perform a similar analysis for the exponent beta, which describes how the magnetization vanishes when we approach the critical temperature from below. So the shape of this curve has the shape t to the power beta, where t is at least proportional to Tc minus t. Well, we know that the magnetization can be found as df dh, and we need to evaluate that at h is 0. We have the following scaling relation for the free energy per site. So this is the same equation that we had above. And now we are going to make this again specific. We choose t small, we choose n large, such that this central element here, this middle guy, is going to be 1. Then this one is going to be 0. And we have then, using the fact that t to the power minus 1 over z is equal to L to the power n, we can find that the last number preceding the h is t to the power minus v over z. Then, if we take the derivative of f with respect to h, we get the third derivative of f, and because of this prefactor and the chain rule, we see that in addition to this prefactor t in the power d over z, we are obtaining an additional factor t to the power minus v over z. If we then recall that the nu is equal to 1 over z, we can replace the 1 over z by nu, and we get the following relation between beta, nu and v. Now note that this involves again a scaling dimension, which is related to the eigenvalue of the renormalization transformation close to the critical point. And in principle, we do not know that value of v, so this is again a relation which does not tell us anything new, but we can combine it with another one, as we shall see now, so that we really get a useful result. And that result concerns the magnetic susceptibility chi, which is defined as the variation of m when I change the field a little bit. And we are going to study that as a function of the temperature. So we see that m is given by this expression, so we have to take an additional derivative with respect to h, and so that means an additional factor of t to the power minus v over z coming out of the free energy, and that results in t in the power d over z minus 2 v over z if you compare it with the expression for the m. So this is the magnetization, this is the derivative of the magnetization with respect to h, which gives me the susceptibility. And then here there is again just a number, so we see that this scales as t to the power minus something, and by definition this is the critical exponent gamma. So we find that this exponent gamma satisfies minus gamma is d minus t v times nu. And if I take this relation for beta and this relation for gamma and I combine them in a clever way, then I can eliminate the v and I find the following scaling relation: gamma plus 2 beta is d nu. But I can combine that with the previous scaling relation, alpha is 2 minus d nu, and that's the form in which this scaling relation is usually presented. And then I find alpha plus 2 beta plus gamma is 2. So that's the second scaling relation that we have discovered. The next critical exponent we study is the exponent delta, and it tells us how the magnetization varies with the magnetic field if we are exactly at the critical point. And the fact that we are at the critical point tells us that we should take t is equal to 0. Now t is equal to 0, so we should do something with the field. We choose the field value small, and we use the number of iterations, the number of renormalization transformations n large, such that L to the power nvh, that's the last argument of the free energy per site, is equal to 1. In other words, the L to the power n should be h in the power minus 1 over v. And so we use the usual scaling relation for the free energy per site. The original f on the fine grid is related to the one after n coarsenings by this relation, and using this value for L to the power n, which occurs here, it's h to the power minus 1 over v, we find that f scales with the magnetic field as h to the power d over v. And so then we can find the magnetization as df dh, And so that scales as h in the power d over v minus 1 times a number, f001. Therefore, we immediately see that 1 over delta is equal to this d over v minus 1 exponent. This last relation involves still scaling dimension v, which generally we don't know. And so in order to obtain a useful result, we have to combine that with two relations that we obtained previously, one for beta and one for gamma. And if we then combine that with this, we find that beta times delta minus 1 is equal to gamma. And that's our third scaling relation. Next, we consider the critical exponent of the correlation function. The correlation function gives us the dependence on the length of the correlations in the system, and it's defined as 1 over r to the power d minus 2 plus eta. D is the dimension, and so eta is a new critical exponent. For the Ising model it's 1/4, so eta is the exponent we are searching for. And we have to follow a rather different procedure from the ones we used for the other exponents, as we shall see. The starting point is the formula for the magnetization, and I will now use the Ising model as an illustration. It's governed by some Hamiltonian which, apart from the field, is just H0. So H0 is the Ising Hamiltonian without a magnetic field, and I have now extracted the magnetic field term from this and put it explicitly in this expression here. Then if we want to find the average value of the spin at some site, J, which due to the translation invariance of the model is just a magnetization, I take the spin at sites J, multiply it by the Boltzmann factor, and I divide by the partition function for the proper normalization. So let us now consider the susceptibility, which is the derivative of m with respect to h. The idea is that we can relate the susceptibility to the correlation function that we are after. So if we do that, we see that in the expression for m that we had here, there are two h's being there, and so if we take the derivative, we get a contribution from this guy and one from that guy. If we take the contribution from the numerator, we see that we get this extra term. It's written here as a sum over k sk multiplied by the sj here next to the exponent. Then if we take this one, which is in the denominator, we get obviously minus 1 over the denominator squared, and then we get the same term, but then with the sum of k sk on the bottom here, and that's multiplied by this term here, and we have set now the magnetic field equal to 0, so that has disappeared now from the exponents. And if we consider these expressions, we see what they reduce to. In fact, we recognize the first term as the expectation value of a sum over k, the expectation value of sk times sj, so that's shown here. And the second term gives you first the expectation value of the sum over k sk, and there is an expectation value of sj by which we multiply that term. And so, putting everything together, it's clear that this is a sum over k of g, k, j, where g, k, j is the correlation function between site k and site j. And if we are in the continuum limit, then the correlations are long ranged, so we don't have to carry out that sum in a discrete way. We can just replace it by an integral, and we get all the contributions of gr of this correlation function over the entire space. And here I have restricted that to values of r that are smaller than the correlation length, and that requires some explanation. In fact, I have written here that the correlation function has this behavior that's true at the critical point. If we are just below the critical point, then this holds only for r smaller than xi. And because xi, the correlation length, diverges at the critical point, this equation is always correct. But normally we have the algebraic behavior for distances smaller than psi, and after that there is an exponential cutoff. Next we turn that into a radial integral, so that gives us a factor of r to the power d minus 1 dr, and then we put in the explicit value for gr, which is r to the power d minus 2 plus eta, and we can do this integral, and the result is psi to the power d2 minus eta, and knowing the value of t, of psi, which is t to the power minus nu, we can therefore write this as minus nu times 2 minus eta. Now we realize ourselves that what we have calculated, which was dmdh at h is 0, that's nothing but the magnetic susceptibility. And the magnetic susceptibility can be written in the form t to the power minus gamma. That was the definition of this critical exponent gamma. And combining that with this result, so these two guys should be the same, we find immediately that gamma is nu times 2 minus eta. And so that's my last critical exponent relation, which is called a scaling relation. Now it's time to wrap up. We have found 4 scaling relations, and they relate the 6 critical exponents, and that means that there are only 2 independent exponents being left into the problem. How can we explain that? Well, we have studied the renormalization transformation and everything derived from the properties of that transformation close to the fixed point. And close to the fixed point we had a series of eigenvalues. In this case we had the eigenvalue lambda and mu. One was larger than 1, the other one was smaller than 1. And associated with those were scaling dimensions. So let's see where we can find those. Here, the y is a scaling dimension that's smaller than 0, and here we have the mu, which is a positive, which has a positive scaling dimension z. Now, all the relations that we have derived, they all depended either on z or on v or on both, but they never depended on y. So for example, here we have nu is 1 over z, no y inside. Then we go to the next one. Here we had a relation for the specific heat, d over z minus 2. So again, no dependence on y. Then we go to the magnetic exponents, and there we see the v popping up, but no z, and certainly no y. Then we have here the gamma. Again, there is a v, there is no y. And then we go to this d over v minus 1 for the delta, no y. And so we see then finally that here there is also no y. So in all the relations which led to these scaling relations, there was only a dependence on either the z or the v or both. And z and v, they tell you something about the eigenvalues of the renormalization transformation close to the critical point. In other words, we could express all the critical exponents in terms of just 2 numbers, and they were z and v. And these numbers are called the relevant exponents. And because we could express all these guys in terms of only 2 numbers, explains why we have so many relations between them. There are only 2 independent, and the rest of course is related. And the relation is expressed in terms of these 2 numbers z and v. The y, which was smaller than 0, so these guys are both positive, is called an irrelevant exponent because it does not influence the value of the critical exponent, and in fact it's a relevant scaling dimension. And that completes the discussion of the renormalization transformation and how it explains these scaling relations. Now, in order to get more information about a specific model, what you need is to perform an explicit renormalization transformation, and that is generally very difficult. But I will treat a few examples in subsequent movies.